Tracking them means I have to apply a strong field.
Fields also the temperature. If you have a super cold sample, you can have quite a bit.
We claim that that's versus track particles without using your.
The depending factor was like you have a particle that has a very small binding energy to the trap, right? And if you have a peripheral collision, you can unbind this particle, right? So the lifetime of the particle in the depending trap would be subject of the right? But there was literature on doing switches of abnormal conductivity and things like that. Those are probably more or you have like an accumulation of these particles in otherwise insulating blocks of matter. You'll see what was.
Basically, put the problem
Well, let's say it's a compensated charge.
Yeah, we're just like. No, it doesn't matter. You can vote.
They also have, well, of course, relation inside volumes of resistance, which is not a little charge, but
small particle, if they are most particle and antiparticle, they will have a high annihilation rate.
It's okay.
sigma V is a cost. Sigma V is a cost.
And the Zoom thing is okay.
So
Okay, so we're happy today to have Ignatios Antoniadis visiting. Ignatios had a very famous advisor. It's John Iliopoulos, known from the gym mechanism. And Ignatios was for a very long time associated with the cold color technique, and then also at CERN, and more recently Karen, and now is associated with Jussieu in Paris. So he's going to talk to us today about the quantum.
Thank you very much. Thank you for the invitation. Again, so to get the title of my book, I will start with the motivation. There's a challenge of the fundamental theory. We describe at the same time phenomena at short distances. Large distances, like close to accelerators, and good observations of the universe. And of course, the two ways to provide complementary information for the same fundamental theory. And what is what I find peculiar is that the information that we get from the universe is that we need substances which are not part of the standard model. Standard model is only a small part of the context of the universe. And the most part is either dark matter or dark energy. So dark energy is it's called energy because it corresponds to an equation of state equal minus law. So it's negative pressure. And the simplest explanation is to have a cosmological constant. cosmological constant is a classical parameter which is dimensions of left to minus 2, like the curvature. And this length can be inferred from the size of the general universe using the quantity of the percentage of dark energy and the Hubble parameter. And turns out to be 10 to the 26 meters. On the other hand, if we want to interpret it as a dark energy, we have to include it to make it put on the other side, and then what corresponds to an energy, we have to divide by the Newton's constant. But then, in order to infer a length, we have to use the Planck constant, h bar, and we infer, and that is what we usually call dark energy units of length, or units, which it's 85 micrometers. It's much bigger. It's much bigger than this, much smaller, so that is also the size of the universe. This is an interesting length because it's near the instances where Newton's law is tested in the laboratory. The present bound is 30 micrometers. Was updated. It was experiment. A group of atoms. And so now we'd like to discuss the value scale. So this is the dark energy scale in energy now. It corresponds to milli-electron volts. The electron-weak scale is where the standard model is located. Also the W, 100 GeV. And then we have the scale of quantum gravity. So these are scales that are known. And I put here two scales that are associated to physics, to physics that it is not confirmed experimentally, but it could be there for various reasons. One is the scale of inflation, which provides a way to explain why units of parts, and also gives a prediction for fluctuations which are consistent with CMB. But we don't know where the scale is. And the other is a scale of beyond the standard model of particle physics. And one possibility is supersymmetry, which again we don't know where it is and if it is there. It comes from natural for fundamental fields like string theory, but we don't know where the breaking scale is. So these are the scales that I'm going to discuss. Then on the theory, there is a consistent theory of quantum gravity, which is string theory. And I'm going to use two main ingredients from this from the theory, which are important for the consistency of the theory. The first ingredient is extra dimensions. Actually, the string coupling, which counts the perturbation theory, can also be treated as an extra dimension from higher, so from my theory. There are the parameters associated with the extra dimensions. And then the second ingredient is that our universe, standard model, matter and gauge interactions will be localized in lower dimensions, lower dimensional branes. And this was important to realize the possibility that this the dimensions transverse to the to the brain can be large, and therefore the string scale can be dissociated from the Planck scale. So that was an important observation in the past. And this allows, of course, the string scale also to be somewhere here. And open new ways to address physical problems with scales. These are some extreme cases. For instance, can be proposed in African region. What is related to can explain the electroweak hierarchy, or it can be an intermediate energies to be related to the scale of supersymmetry breaking, transitive scale, this one neutrino scale. Despite the fact that the theory starts in high dimensions, it's quite unique. Once you go to lower dimensions by compactifying all these extra dimensions, then one finds several parameters which correspond to expectation values of the various so-called moduli fields, which parameterize the sizes and the shape of the compactification manifold. For a long time, initially, Augusto thought that if one find a way to stabilize this moduli potentials, then one could determine the vacuum quite uniquely. However, what happened is that this standard way that was found to fix these parameters by introducing discrete fluxes. So these fluxes are generalizations of magnetic fields, but for higher order tensors, which exist in string theory. And in the process of compactification, there is an arbitrariness. One can introduce such these fluxes which are discrete because the space is compact. And it turns out that the stabilization of moduli is given in terms of these discrete parameters. So at the end, the module stabilization gave rise to a huge landscape of vacua. And the question is how to determine and what are the criteria to determine the standard model landscape. In particular, we would need some extra input or guidance principle that would allow to select from the physical theories. Now, due to the Swampland Program, can contribute in this direction. Although, as it was phrased, that mostly phrased as the possibility to find the criteria under which effective field theories can be consistently coupled to gravity, in the sense that it can come from some fundamental theory of gravity, or particular string theory. And it was realized that some of the obvious criteria, which is anomaly cancellation, for instance, for parallel fields, is not a sufficient condition. And the consistent trivial completion can bring more non-trivial constraints. So the effective theories which are not part, which do not satisfy this constraint, are part of the Swampland. So the argument, of course, there are no proofs for it's difficult to make proof for such statements. One can sometimes make proofs within string theory. So this the criteria is mostly based on conjectures that are supported by arguments based on the knowledge of string theory or gravitational physics, in particular black hole physics. So the conjecture that I'm going to discuss today, which related to the talk, is the distance duality conjecture, which states that in the landscape, if you are at large distances in the field space, in other words, I will call this field phi, so phi can think of it as a canonically normalized field, and you look at the distance at the distances in the field space, which are large. Larger means compared to the Planck unit, to the Planck mass. Then the statement is that at such large distances, there is something going wrong, the validity of the theory, and there is a tower of states that become light in an exponential way. In other words, their masses are exponentially small with the distance, with an exponent which is of order 1 in Planck unit.
So Ignatius, I have a question here. So to what extent is this due to string theory or just quantum gravity in general? Because
This is mostly string theory.
Because this seems to me that it's just due to the fact that string theory is in 10 dimensions and you got to by 10 dimensions to 4. So you have a lot of flat directions. And so you can have all these moduli around. But let's say I had a quantum gravity theory in 4D where I don't have any flat directions. Would something like this survive?
Yeah, the question is what is this quantum gravity theory? What happens if you consider distances which are bigger than the Planck? Yeah, that's it.
Yeah. So this one just relies on it's more. The evidence is more.
And also there is another input here. There is a landscape. So there are fields that you can move this vacua by even in a discrete way, but by modulus. So
all quantum gravity theories have these fields.
So this argument will be based on stuff.
But isn't this just the statement that moduli must be stabilized for the theory to be reasonable?
No.
Well, if phi disappears,
we're stabilized. Now we know that we can stabilize on moduli, but in terms of discrete parameters.
so what is phi? Phi is not a modulus. What is it?
It's the value of the modulus, of the stabilized modulus, but it can. There are discrete values of it because there is a huge number of vacuum.
Right.
And these distances are the distances in this discrete values.
Okay, so this is saying it's not acceptable to have stabilized moduli with values of order the Planck mass.
You can interpret it in this way, but what I'm trying to do is to make physics out of this.
All right.
What determines alpha?
I will see in some examples. So that was the first part of the conjecture, the distance. And the second part is this duality, which states that this tower of states provide a weakly coupled description of the theory up to some cutoff scale, which is called species scale. This was introduced by Valley back in 2007. And his observation was that in the presence of many particle species, the strength of gravity becomes stronger than the Planck mass, and it is in mass units. The strength of gravity is reduced by so the effective Planck mass is reduced by the square root of the number of species. So by species can be any particles which are stable or which have a weight which is less than their mass. That's the definition. And this argument there are several ways to argue about this. One is by black hole physics, that if you you can show that for lengths less than the inverse m star, the system collapses to black hole. Because it becomes that length becomes less than the short range.
But that
So-
assumes that the species don't have any repulsive forces. There's some.
Yes.
Well, when just a naive kind of renormalization of the scalar gravity, scalar curvature, just due to the loops of matter fields, just consider that this will pop up in front of our.
Yes,
and,
that's true. Yeah, that's true.
and it's purely perturbative in some sense, right? And it doesn't require.
Yeah, these are this is the case. So these are two particular examples here of this of what is this scale. So one example is where you have an extra dimension which we compactify. So this is in that case, the number of species are the Kaluza-Klein model for the excitations up due to a large dimension. And the species scale is just the high dimensional gravity scale, which is related to the Planck mass by I'm going to put here instead this one unit. No, sorry, it's correct. This is the Planck mass in proton dimension for the extra dimension, which is related to the four-dimensional Planck mass in this way, where this small m corresponds to the compactification radius, to the compactification scale, so it's the inverse radius. And here, going back, the distance phi is the logarithm of the radius. And the reason is that the canonical normalization, if you start from a high dimensional theory, then the radius, let's say 5 dimensions, then the radius is the extra component of the metric, and the field that the canonical normalized field is precisely the logarithm of the radius. There's a kinetic term that you obtain with dr of the R. So this provides one example. Another example is the power of string excitations, of course, which this multiplicity is exponential multiplicity. In that case, m star is the string scale, and the distance is the logarithm of the string coupling. So the reason again is that the string scale, the Planck scale, the Planck scale is the inverse of the string coupling times the string scale. So and the string coupling is associated with a field, which is the dilaton field, and again the proper distance, which is the canonical, which corresponds to the canonical normalized field, is the logarithm of the coupling. So this is one way to see. Another way to see it is that if one considers the string excitations, and one asks at what point the heavy excitations acquire a width which is bigger than their mass, you find that this happens around 1 over z string, the number of species. So the number of species are the number of string excitations, which can be considered as particles which have a width less than 1. So these are two examples, and now there is a conjecture which is argued by a string of amplifications, not only perturbative string of amplifications, but also within a theory which captures some non-perturbative features, that says that these are the only two possibilities to have large distance in the scale. So that is the conjecture, and now what proposes that the smallness of physical parameters that have in physics could be an indication that we live in a corner of the landscape which corresponds to large distance. So that is, this would be, of course, you cannot exclude the possibility that there are other ways, that there are cancellations, but that's what with fine-tuned conditions. But this is one possibility. So we'll try to apply this to particular small scale in physics. So the first example of this is we've noticed it back in '88 when we're looking at four-dimensional constructions of four-dimensional strings. And at that time, the way to construct string fields were using Gaussian two-dimensional Gaussian model, with two-dimensional bosons or fermions. And that was an observation that in the spectrum that we were getting, if there was a particle which has a quantum number for gravity, in other words, the spin very hard, and it's vector, and you try to make the mass much bigger and much smaller than the Planck mass, the string scale. Then the observation was that the consistency of the theory implies that there is a tower of states above it with the same quantum numbers and masses that increase linearly with the empty half. So K is an integer on top of the gravitational mass, and then with some other integer which was not too large. So what we had tried to do at the time was to bound this n. And for free fermionic constructions, we have found that we could show that n is less than about that. So depends on the construction, but it was a small number. While for bosonic lattices and using bosons, then n had to be less than about 1,000. So this relation, it's useful. It can be written in this way. It will become clear later. So obviously, one can interpret n is related to a compactification. Every fact is related to a compactification radius, and the scale is n3 cap times a parameter, which is precisely related to this n.
So this makes no assumptions on the mediation of Susie breaking?
No.
So you assume that
No, that's the free spectrum. That's the free spectrum.
so it could be gravity mediation, gauge mediation, no problem.
Yeah, the mediation is later on. I mean, that's these are the empty cap is this the gravitational spectrum that get the particle that get directly at the tree level using this CFT for field theory, but it's out so recently, using this distance conjecture, there is a group of APAC proposed that, there is a dark dimension associated with the dark energy. The dark energy is a small parameter, and the proposal was that this small parameter could be related to the fact that you live in a large distance in the landscape. So n is a compactification scale or a string scale. So it's a scale that associated to a tower of light particles. which should satisfy a relation like this, where lambda is a proportionality factor which discussed later on, and lambda is the cosmological constant to the in Planck units to the power a, where a has this is bounded in this way. Now, the first point to justify this relation is that the distance is proportional to the logarithm of the cosmological constant. This relation was shown in Adi de Sitter vacuum and was extrapolated to de Sitter. So that's this was one assumption. And then the next step is to bound the exponent. The upper bound, 1/2, is actually unitarity bound in the Sitter space, which was in the thesis of Iguchi long ago, which says that the massive spin 2 in the Sitter space should have a mass which is bigger than the Hubble constant. So the square by lambda. So the 1/2 is this one. And that's unitarity. In other words, if you don't satisfy this bound, then there are negative normal states. The lower bound is an estimate of the contribution in the cosmological constant based on the fact that there is scale m. Then certainly there are contributions to the vacuum energy which go like n to the 4. That's for the so unless there are cancellations among these contributions, then there is a lower bound which is n to the 4, and that's how this 1/4 comes. Yeah. On the other hand, now we put in observation, we know that lambda is 10 to the minus 120. The scale m, obviously, the scale m is too low, so to be a string tower, so it has to be a line tower. And the compactification scale must be bigger than the 0.01 electron-volt, which from the Newton's law that I saw before, which corresponds to 30 micrometers. So this implies that A is very near to 1/4. In other words, there is no room to introduce more than one extra dimension, because if there is a dimension at this scale, then due to astrophysical constraints from supernovae, you cannot have more. You cannot have more dimensions. That's one. Moreover, the species scale, which is now the 5-dimensional Planck mass, is about 10 to the 8 GeV times this coefficient. Now, this coefficient lambda also it was argued to take these values to be in these range. The upper bound comes again from the Newton's law, and the lower bound was just an argument that if lambda is too small, if lambda is too small, then it amounts to change the power here from 1/4 to make it 1/5. So that's how the argument of that.
So the reason the old ADD wanted it at a TeV, that's why it was ruled out. So here you put it at 10 to the 8 and it can be ruled in. Yeah.
These supernova constraints, are these like the KK states can be produced, but so the KK states for just one dimension are allowed, but for multiple dimensions, there's just too many of them.
For 2 dimensions, they imply a bound about 10 MeV for the size of it, for the compactification state. And for M star, it's 1000 PV. And more than 2 dimensions, then the bound is relaxed, but then it cannot be used here because here you need related the compactification scale is related to the scale of cosmological. The two dimensions could be, but they're excluded from the I mean, to be such large. There are, before going on, I'd like to just mention two more applications this proposal. One is that one can, because of the scale, it can be this scale is also consistent with, I mean, so the order of the neutrino masses. So it allows to introduce the right neutrino in the bank, like the proposal in the case of two extra dimensions in the past. And actually, since that time, since the large extra dimensions, there are several works that appear from time to time. They do the analysis of oscillations in the presence of extra dimensions. They take just simplicity one extra dimension. So that was, for instance, the recent analysis introducing three bulk neutrinos, and they found that the bound at the quantification scale should be less than 40 0.4 micrometers, which corresponds to a quantification scale bigger than 2.5. This, so if one wants to implement, which is natural way, bulk neutrinos in this such a case, then lambda, this parameter is more 10 to the minus 3, and the 5-dimensional gravity scale, the speed scale is 10 to the 9. Another interesting application is that this proposal provides candidates for dark matter. One is through the primordial black holes, but it's 5-dimensional. In other words, they have a Schwarzschild radius which are smaller than the size of the extra dimension, which is the micro scale. And this, so the Schwarzschild radius is in this range, it's less than micro, so that's 5-dimensional. And the observation here is that if 5 dimensions, a black hole with the same mass lives longer, and therefore this extends the parameter space, the range of the parameters that mass that can use this black holes to explain the dark matter 100%.
Did you also discuss how they're produced in your paper?
No, how we can do it. There is a whole literature. Yeah. So that is the mass range. Let's say for 4-dimensional. This on the left is the 4-dimensional black holes. So the allowed region is here. This parameter is the percentage. No? So if you look up, if one wants to explain 100%. The dark matter. So this is the allowed rates. On the low part, they're excluded by evaporation, goes too fast. And there is micro. Now, in 5 dimensions, so if you go to 5 dimensions, then you open up this part. So that gives about 3 orders of magnitude.
Yeah, because, sorry, if I could just ask it again, because in 4 dimensions, you need some spikes in the inflationary potential, so that the energy density can be much bigger than, say, 10 to the minus 5 to have fluctuations. Enter the horizon and form 4D primordial black holes. Does the 5D story help with that, or is it the same story?
There is an issue there with inflation. I would if you assume 5-dimensional, the 5-dimensional physics, we can assume the same thing, but it is not clear.
I see, so you can do the same thing.
The other possibility from the group of Rafa was that the dark matter could be the Kaluza-Klein excitations of the graviton with decreasing mass due to internal decays. I mean, the Kaluza-Klein extensions in principle they decay because the momentum is not conserved, is violated. The conservation of the momentum along the extra dimension. So, in order to use the Kaluza-Klein extensions as dark matter, you need to assume that the violation of the Kaluza-Klein momentum is in some particular range. Otherwise, they too fast or they live too long. So they made the observation is that because of the internal decays, the mass of the dark matter peaks, let's say peaks around the scale, which changes, which decreases due to the decay from the time, let's say, of matter radiation quality to today, from MEV at this point to 50 keV today. So this can realize this proposal dynamic dark matter. I think was deemed to also appears that if you put the range of parameters, you can argue that the experimental signals could be exactly the same between the two cases. What corresponds here to in black hole, the decreasing mass would be that the black holes accrete from the medium. And before we move on to this question, I'd like to discuss now another issue there, which is the inflation, how this scenario could work. It was observed in the past that in the presence of extra dimensions, one should be careful when compute the inflation scale. If the scale of gravity changes because there are many species, then, for instance, by measuring the ratio of primordial gravitational waves, you cannot determine the absolute scale of inflation, but you can determine only in terms of the Planck mass. But if the Planck mass is reduced, then you cannot really infer what is the absolute scale of inflation. You want to face the different in cosmology, all the observables are dimensionless. So the scale is put either by the Planck scale, or if the Planck scale changes, then put to take into account this. So in the presence of extra dimensions, one has to take into account here to replace the Planck mass by the scale of gravity, which is reduced by the number of Kaluza-Klein excitations. So M star I is the strength of gravity at the time of replacement. So if you take this effect into account, you consider the Kaluza-Klein excitations of an extra dimension with the compactification of the electron volt, then one finds that the scale of relation is about 10 to the 17. On the other hand, this bound is not there is another bound which is much more restrictive, and which has to do that if you assume that at the time of inflation the radius is fixed at the micron, then there are excitations of the graviton, and in particular mass 6.2, which have a mass which is much lower, and therefore the Iguchi bound, the unitary bound, could be violated. So one has to, if one requires with a given compactification scale, the Iguchi bound implies an upper bound for the cosmological constant or for the Hubble constant that should be less than the mass for the spin 2, so less than the compactification radius. So if you translate it here, back there, you will find that the scale of inflation should be less than 100 GeV, which, okay, we could imagine it, but it's better to find some other way to do it. And the nearest possibility is to let the extra dimension expand with time, at the same time with the function of the three space dimension. So if you ask the question, how many equals you require, starting from a dimension that it was of the order of the ultraviolet cutoff of the species scale at that time, to reach the micron scale, you find that you need about 42 equals, which is interesting. And actually, it's much more interesting because if you translate the units from 5 dimensions, 4 dimensions, one has to rescale to take into account the change in the Planck constant, or if you want that the 5-dimensional Planck scale, the 5-dimensional line element metric is related to the 4-dimensional metric by rescaling the size of the radius. So if you start with the sitter here and you make the in 5-dimensional units, you see that the 4-dimensional metric is not the sitter anymore. And actually, after 5-dimensional inflation of any impulse, the 4-dimensional metric is expanded by 63 equals. So, because there is a factor 3n over 2 due to the artificial scale. So that is an interesting idea we'll try to explore right now to see if
Why doesn't this 5th dimension keep expanding? So you stabilize it?
yeah, okay, there are 2 issues. First, you have to stop inflation. The inflation can be stopped in the same way, like in 4-dimensional inflation, by producing an inflaton that has a potential that there's some flat reaching the potential when it stops. When it stops, of course, the radius has the right value, but then you have to stabilize it, you say. So that is the second part of the problem. I don't have a solution again. Although there is something interesting that for one extra dimension, which corresponds to a field that is running like exponentially, so you obtain a quintessence type potential, which with an exponent which is very near to the present bound between 0.6 and 0.8.
So you're saying it's still moving today, but very slowly.
But
Growing very slowly today.
Doesn't that affect all the couplings?
But very slowly.
that's why I was to find a way to stabilize it. But okay, that's the other question, of course, is how to inflation and you have to populate the 4-dimensional universe. So the easiest way to do it is by assuming that this 5-dimensional integral is the coupling to standard model brain, like we have a coupling type. In which case one has to impose a condition that the decay rate to standard model is much bigger than the decay rate into gravitons. And you find that this gives you upper bound of the mass of the equation around 2D. So let me now move on to the supersymmetry breaking. So the gravitino conjecture. Just remind you that was the linear relation that we obtained on time. Recently there have been a proposal that the gravitino conjecture, which is essentially the same relation that when the gravitino mass is low, there is a tower of states. Compactification again. The strength scale is too low. By imposing not a linear relation, but a relation with an exponent n, when n must be positive. When cap goes to 0, this will go to 0. So the now becoming more precisely into the question what is and how the entry cap is related to the supersymmetry breaking scale. So the first step is that supergravity, it's flat space. Gravitino mass is related to the scale of supersymmetry breaking by this relation, where M SUSY now is the expectation value of the next term or the term of the expression. So even if the supersymmetry breaking scale is high, if there is a supersymmetry at the fundamental level, the breaking scale should be less than the species scale, the gravity scale at high dimensions. And of course, because of this, bigger than half. Again, this M SUSY does not determine what are the superpartners because it depends on the mediation mechanism. So, for instance, in gravity mediation, the soft masses goes like M SUSY squared, and therefore they are of the order of the gravitino mass. While in gravity mediation, in gauge mediation, the Planck mass, which is implicit here, is replaced by the messenger scale. In the case where the messenger mass is of the order of SUSY scale, then suppression is just loop factor. So the proposal was to combine this gravitino mass conjecture with a dark dimension. So we have two small parameters here, one is the cosmological constant, one is the supersymmetry breaking. And therefore there are, you can assume that both of them are small because therefore they should be related to some tower of states, which is low. Then there are two possibilities. The first one, which is the most interesting, is to have only one tower. That the same tower that generates the dark dimension described before would also be responsible for supersymmetry breaking. And the second possibility is that there are two different towers, M1 for the dark energy and M2 for the supersymmetry breaking. So I will describe first the case of a single tower. In the case of single tower, since this tower determines both, is related both to the cosmological constant and the supersymmetry breaking, you can relate the two. And you obtain a relation of this type. So, n here is the the parameter, the exponent is this in the tower of supersymmetry breaking. So this relation between the cosmological constant and M3 actually can be identified as the leading non-vanishing power of the super trace M square in effective supergravity. So that this implies that n is either integer or half integer, because the powers are even. And for instance, for k equals 0, you obtain the quartic divergence, which should be 0 in supersymmetric field. And then we have k equal 1, which is of course quadratic and so on. So requiring that the supersymmetry scale is less than m m star. Now m star is fixed, is the scale that I mentioned before of the dark dimension. It's 10 to the 9 GeV. One finds that n should be less or equal to 2. And then when you impose that the supersymmetry scale is bigger than about 10 TeV because of the LHC constraints, then you find that n has to be bigger or equal to 1. So there are just 3 values possible: 1, 3, half, and 2. For the case of n equal 1 is quite interesting because okay, the M3 half is of the same order as the compactification scale, the electron volt, like excitations of gravity, and the SUSY scale, the supersymmetry breaking scale, is of order 100 TeV, which means that the mediation to the standard model should be rather gauge mediation. The other 2 cases give a supersymmetry breaking scale which is high, near the species scale, and the gravitational mass is between ZV and multiple. The second possibility, which is in which we have 2 different towers, although one could think in the beginning that there would be much more, we have much more freedom, it turns out that it is also very restricted. In that case, okay, there are 2 towers, so I has to, for the species scale, one has to take into account both calcium stations. And now you put experimental bounds. The second compactification scale must be bigger than 10 MeV from the supernova. The supersymmetry breaking scale should be bigger than 10 TeV. And then you find that only 2 possibilities survive. Any n bigger than 1 is excluded for p extra dimensions associated to the supersymmetry breaking. So these are the 2 possibilities. The first possibility is this power to be 1/2. In that case, the second compactification scale is linearly related to the supersymmetry breaking scale. And then 3/2 is okay, as before. So the supersymmetry breaking scale is now related. It can be up to 10 TeV, but yeah, for M star that becomes a bit lower than before. And the second possibility is when there is again 1 extra dimension associated to the supersymmetry breaking, in which case one obtains that the second dimension is about 20 MeV, and the supersymmetry breaking is time.
In what sense are these natural predictions? Because the lambda 3/2 parameter, you have to take it small, right?
Yeah, but that's why I gave you small means
You have 10 to the -5.
over kappa, yeah, there are two parameters.
Yeah,
So the second is a bit tuned. But I don't know, you know.
what's
these
the
are-
origin of that?
I mean, I gave you in the beginning.
What's the
that's why
origin of that
also-
coupling? That's
yeah.
why.
That's why I gave you also here, okay, this was found based on the string prediction.
I
And
see,
you
so it's
found-
one over n, it's one
Yeah,
over
yeah.
n, that
So
coupling is,
you find 10⁻⁴.
I see.
You know, it's,
So it's not of order one, it's of order one over n.
I mean, it is models. So that is a summary. We discussed a bit the generalizations. We found 5 viable solutions. And I classified them here that in a way that the relation between at what time, for which cases, either the gravitational mass or the supersymmetry breaking scale is linearly related to the conductivity scale. It can be either the case of one extra dark dimension, or it can be the second dimension. These are the 3 possibilities, and the other 2 were the possibilities in which the supersymmetry breaking scale is high. So these 3 possibilities in which there is a linear relation between the gravitational mass or the supersymmetry breaking scale and the conductivity scale can be realized by imposing self-Schwarz boundary conditions, in which the high dimensional field is periodic up to an asymmetry transformation that breaks supersymmetry. And the way that it happens is that there is a shift of the KK momentum, to the Kelso-Klein momentum, by a parameter which is proportional to the arc size. So for instance, the gravitational zero mode gets a mass proportional to the arc size, and this lambda parameter is as a charge. If one takes, for instance, the simplest example, which is the temperature type breaking, which is the Helmholtz periodic, and get 1/2 into the frequencies, then the charge is 1/2. So this the minimal possibility, which is the most attractive, is just the case that you have only 1 tower and 1 dimension. And then in which case the vacuum energy scales like 1/r⁴, consistent with the bar with the parameter 1 to the exponent 1/4 mentioned before. And in string theory, as I said, it can be generalized. It can be in principle. This linear relation can be realized by self-Schwarz boundary conditions. Now, this was studied in the case of brains. It can be generalized in the case of brains. However, the result that we found is that when the boundary conditions break supersymmetry with respect to the dimension which is transverse to the brain, as we want here, there was no effect on the brain. The brain was still closed under supersymmetry. So there is an open problem how to introduce a breaking also in the brain, consistent with the supergravity relation between m3½ and the supersymmetry breaking scale. There is no example of this. It's an open problem. On the other hand, the solutions in which the supersymmetry breaking scale is high, they can be obviously realized because you can break supersymmetry by the positions of the brains, but you can have it to lowest order in the bulk, and then the transition will be by gravitational interaction. So you will obtain automatically the relations that one needs. One could also imagine a situation in which the brains have only nonlinear supersymmetry. In other words, the spectrum is not supersymmetric because you combine, for instance, branes with orienticals, which preserve the supersymmetry that is broken by the branes, and which is realized nonlinearly. In that case, we have nonlinear supersymmetry, but still, it's well. About to finish. So also I can write the effective theory, for instance, in this in the cases of within supergravity that realize the parametric relation between the cosmological constant and the gravitational mass for a Keller potential which has a standard formula. You have three fields can interpret the three tori, and correction to the Keller potential is a constant which corresponds to a loop or parameters, depending if you look at that way, that would be, and the constant superpotential. In that case, you obtain a potential which goes like parametrical, the same like n3 factor to the 4. And in particular, this also describes the self-Schwartz type models with throughput. So STU is S is the dilaton, and T equal U. You have one dimension, one extra dimension. You obtain the spectrum in string units. You obtain the spectrum 1 over R. But the gravitational mass is linear in compactification scale 1 over R, and the potential goes like 1 over R to the 4. So this is a translation of units between the Planck unit, the Planck frame, the Einstein frame, and the string frame. So the conclusion I like to conclusion. So I thought that the message here is that the smallness of some physical parameters might be a signal that we live at large distances in some corner of the similar scale, and such parameters could be, for instance, the scale of dark energy and the supersymmetry rate. And it allows to generalize the dark dimension proposal by incorporating the supersymmetry breaking. The dimension of possibilities.
The distance conjecture, though, is talking more about displacements, right? In the field. And you say we live in a.
It's a static. It's static. Is that some the physical parameter is determined by the expectation value of the modulus that has an expectation value bigger than the Planck.
But relative to what? Because
The
if
Planck, this is exactly what happens in the case.
I tend to agree with Keith. I think it's referred to a theory defined at origin, and you'll say, oh, if my fields, if I discuss my theory at a large distance, behavior there, that's not the discussion. Yeah.
So the distance, the unit of distance is the Planck length.
Yeah, with respect to the theory actually defined at origin. So that's where the large parameter.
what is the origin? Where is how do you define where the origin is?
Why you say to define the origin?
Because you say if we're at phi equals 10m Planck here, I say, okay, but this I'm calling now 0. 0 here I can redefine to be 10m Planck as well, right? For some other field with just a redefinition by constant.
Yeah, but it doesn't depend where you put the origin.
But that's why I'm saying then it should be displacement. That if you have to talk
But
about.
nothing moves it.
But you're talking about relative positions in field space.
I think it's written as delta phi is of order n Planck.
Right, that's what I mean.
Yeah, so I think it's.
Large field
displacement.
expression
That's why, for example, the criticisms for Starobinsky is that, well, the vacuum is at zero, right? You're calling that position zero, but you have to start at some very large field value.
Yeah, although they are dynamic field that moves.
In that case, it's dynamical, but something you have to be able to define two different points,
Yeah.
right? So that's what I'm just asking. The smallest of the parameters tells us that we live in a large distance corner.
Yeah, it means that the corner means that there is somewhere the origins, if you want, are consist of solutions in which all the fields have expectation values of the order of black matter. So large distance means with respect to these solutions, you look far. And then necessarily something happens, there is a tower of states which blow light.
But large expectation value relative to something.
To the Planck scale. I mean, the unit, there is only
Yeah,
one unit.
there's one unit.
So you can, in the space of vacua, you have some, the origin is defined by the vacua where all the parameters or the fields have the same expectation value of this order of the Planck matter.
Other questions? The example that you had, where you said there's no tree level effect. Brain example, so there's no tree level effect on the boundary, but then wouldn't there be loop effects?
We studied, I mean, at that time we looked at the loop effects and it was not, we could not obtain, it was a present. That's why at that time I proposed to realize this heavy gravity. Okay.
So for your light gravitino scenario, what's the lifetime of NLSP? You have M3 out like electron volt.
Well, it depends what is the, I mean, if the LSP you want to be the dark matter, no, we don't require such enforce such requirement because dark matter can be, as I mentioned, can be the consequent extensions of the gravity.
Sure, but do you expect some cosmological abundance of the SUSY renders?
That's less, yeah, it should be less.
Or what's the lifetime? I just forgot when the SUSY mass is 10 TeVs and gravitino mass is light, then the lifetime is small, right? Is it or
Yeah, it's small.
small?
But I mean, you're worried about having a lot of 0.1 EV particles.
Oh, for energy injection, early time.
But people did put limits.
Oh, but that's very early,
Yeah.
right? If it's bigger than 10 TeV, I mean, it's before nuclear synthesis.
That's what. Also, they remind me. I mean, my memory is not so good. It goes back to your scenario. Dimopoulos and Wally with 2 extra dimensions. You have to be very tricky with early cosmology. There was like a few hit universe above 30K MeV, and then there are problems and so on. Here it's milder, I understand, because it's one. What's the sort of maximum temperature you can tolerate here?
The maximum temperature can be up to inflation, but the lower.
It's interesting, right? So you're saying that for one extra dimension, I have no problem, right?
Although there is this question, there is the question if you want to implement inflation, there is a restriction on the inflation scale.
I think as far as I remember Salas's paper, there was a problem even with like having the universe hotter than 100 MeV with 2 extra dimensions because you populate way too much, these extra states. And there is
Because
like-
in that case, the scale was very low, it was TV.
right. So you're saying that
Here the
That-
scale is high, 10 to the 9 dB.
but you
So
still have
there
a
is very-
you still have a tower. Right?
Yeah, you have a tower, but, as I said. If the tower is fixed, the mass is fixed,
Yeah.
then you cannot have inflation at a scale higher than 100 dB. That's a
I'm
problem.
happy to discuss just the thermal universe.
The thermal, yeah, that's different.
No inflation. What's like, understand that your scaling is 1/m. The rate populating is going to be scaling as 1/m star cube, right? Or
Yeah.
something like that.
The-
And if I have way too high temperature, I probably have some order 1 population of these guys, right?
the way that, in that case, the way that, for instance, these dark matter scenario with Kallisplan stations work was proposed is that you assume that the brain is already populated with standard model, for instance, from case of and but then you can generate what it's already at thermal equilibrium at some temperature, and then you produce a Kallisplan stations. So these Kallisplan stations, which are produced, and they can decay one to the other, but with some constraint on how much. They populate the spectrum, which is peak around a scale that decreases as the temperature decreases. That's a dynamic of that. That's how we analyze this possibility.
Oh, so you're not relying on a single dark matter
No.
candidate, you're relying on this whole KK
Yeah,
tower.
the whole KK,
Oh, I see.
and because you assume that there is already the thermal equilibrium for the standard model, this produce already KK, and you can compute the spec. Fix somewhere. And then it is not.
But the higher states aren't stable, right?
Yes, so that's why you start. It starts with MEV. The mass. Yeah. It starts with a mass with peak up around MEV. Because it cannot produce heavier. And then it goes down.
So the heaviest is an MEV.
Yeah.
Don't you get into other types of problems? What's the lightest then?
I mean, there is a spectrum, no, but it peaks at that mass scale. And as you go, as the temperature decreases, it moves because the KK decay. But the decay in a way which is constrained, no? Because they imposed a bound, not a bound, a region in the amount of KK violation and KK number violation. And that's
And
what's
these
allowed.
aren't fermions. These
Now, if you ask me whether this is natural or not, then,
they're not fermions, so,
no, these
okay, so some of the
are
problems,
gravity.
huh?
These are gravity, it's spin 2.
Some of the problems that you would get with lighter fermionic dark matter, you don't have. There's no Pauli exclusion. And what's the highest temperature you get? in the standard model sector?
It's that.
The highest temperature
Yeah, at what,
ever.
visit. You need a model for this different. I mean, in principle, you can start with and start.
Okay,
You don't know, then it depends how you do.
how you come out of inflation.
But then your tau is 100% off away.
Hmm?
Then if you start at star, the temperature star, then your tower has to be 100% populated.
If you start with a star, then
Yes.
you have to, that's what I,
And then
because then you have to do 5 dimensional space.
okay, let's exit from the inflation and let's freeze the dimension, right? If the temperature is star, you still have like enormously more energy stored in that sector compared to the standard model because the sheer number of the consequent ones is very large.
The example of consequent states in reality, but they are produced in the bulk. While
They still carry energy.
the brain, yeah, the brain, I mean, the standard model is on the brain. So,
Yes.
you know, you can have both. That's what I do. To produce standard model particles. There is enough room to make it much larger. The standard model is much larger.
Okay, if there's no other questions. Let's thank Ignatius again.